In this video, I thought I'd go ahead and solve a problem that had been proposed to me. The problem, as shown in the diagram, consists of a cart or a car, something that has an initial velocity v0 to the right, and it's going to hit this damping system, which could be thought of as the bumper of a car or a buffer system at the end of a train track, and it's going to compress this by an amount x, and I've drawn the coordinate x at the top. And the idea is we'd like to know what is the maximum deflection x, and how long does it take to reach that maximum deflection or displacement. We're given the following properties. The mass of the cart is equal to 2,000 kilograms, so 2 times 10 to the 3 kilograms. The stiffness of the spring is equal to 60 newtons per millimeter. And I should mention I've drawn it as two springs, each of k over 2 stiffness. But springs in parallel, the stiffnesses are additive. So you could think of this as a single spring of stiffness k. Same thing. This is 60 newtons per millimeter, which is 60 times 10 to the 3 newtons per meter of deflection of the spring. And the damping of the damper, the damping constant is 20 newtons seconds per millimeter. Newtons seconds per millimeter, which in SI units would be 20,000 newtons seconds per meter. The initial velocity, v0, is equal to 10 meters per second, which is exactly 36 kilometers an hour, or approximately 23 miles per hour. We, of course, know that the critical damping constant is equal to 2 root mk. We know that from a previous video. The link should be up above now. The damping ratio, which is zeta, is equal to the damping divided by the critical damping. We also know that omega n, the natural frequency, is equal to root k over m. We've shown this previously. And the damp frequency, I'm going to do it here just to save space, is equal to omega n, the natural frequency, times 1 minus zeta squared, where zeta squared is from 0 to 1. So the damp frequency is always going to be less than the natural frequency, which kind of makes sense, because when there's damping involved, the system wants to vibrate slightly slower than when there's no damping. All right, let me just put some lines here and divide this off. All right, so we've shown in a previous video that the displacement of a damped system, x of t, can be written as x of t is equal to e to the minus zeta omega n t times some constant a1 cosine omega dt plus a2 sine omega dt, where omega d is the damp frequency of vibration of the system. We'll call that equation 1. All right, we have two initial conditions. What is the velocity and what is the displacement at time equals 0? Well, the first initial condition, we'll call it IC1, is that the displacement is 0 at time equals 0. So x of 0, x at time 0 is equal to 0. And you should be able to see by inspection that this means that a1 is equal to 0. Okay, we'll call that equation 2. And then if we substitute that back into equation 1, this would imply that x of t is equal to a2 e to the minus zeta omega nt times, sine omega dt. Call that equation 3. If we take the time derivative of this, x dot, we get a2. Now we've got to use the chain rule. So we take the derivative of this times this plus the derivative of this sine times the exponential term. So the derivative of the exponential term is just minus zeta omega n times e to the minus zeta omega n t sine omega d t. Let me just do it on the next line, plus omega d. So the derivative of sine is omega d times cosine. So it's omega d times e to the minus zeta omega n t times cosine of omega d t. We'll call this number 4. All right. So the second initial condition, IC2, is that the velocity is equal to v0. So x dot of 0, substituting it into equation 4, gives us, let's see the easiest way of doing it. Let's just write it out. A2 times minus zeta omega n. The exponential at 0 goes to 1. The sign cancels. So in other words, this term is 0. We don't need to worry about it. The second term, this becomes 1, and this becomes 1 at time equals 0. So we're just left with omega d. Did I say that correctly? No. I need to. So you end up with A2. Remember, we can ignore this term because the sign of 0 is 0. So it's just times omega d. This is 1, and this is 1. So we're going to say times 1 is equal to v0. Okay? This implies that A2 is simply v0 over omega d. We'll call that number 5. All right, so now if we substitute equation 5 into equation 3, we get that x of t is equal to v0 over omega sub d times e to the minus zeta omega n t times sine of omega d t. This is our expression for the displacement x as a function of time. And I guess at a certain level, this assumes that once contact is made, that the two stick together. As we'll see in a second, it doesn't really matter because we're not going to look at it that long. But fundamentally, if the two stuck together, this would be the equation x as a function of time. Right, well, let's have a look at this quickly. Let me just draw it out over here. See what's going on. So we've got harmonic motion from the sine term, but we've got a decaying exponential here. And so what happens is we end up with something, let's see if I can draw it accurately, or accurately enough. So we've got some sort of an exponential decay like this. And then, let me draw this in red. Starts at 0. We've got a sine function, something like that. My hand is a bit shaky. I apologize. All right. And what it's asking us is, what is the maximum deflection x, and what is the time it takes to get there? So this would be x on this axis. The y-axis we call the displacement x. And on the x-axis, this is time. It's actually omega d times time. All right. And what do we know about the sine function? We know that it's 0 at time 0, because after all, we're dealing with the sine function part of this. This would be pi. This would be 2 pi. This would be 3 pi. In other words, it crosses the axis. It's 0. X would be 0 at multiples of pi, at n times pi, where n goes from 0 to infinity. Okay? And what the question is asking us is right here. Oops. It's saying this is x max, or this is t max. In fact, to be clear, it's omega d times t max. And this would be x max over here. And it's asking us, what is it? What is the height of that peak? And we should be able to recognize that this is pi by 2. In other words, when omega d times t is equal to pi by 2, this is when we get x is equal to x max. Does that make sense? So we can solve for t max by saying that, I'll do this, let me just do this below, the t max part. So we know that omega d times t max is equal to pi by 2. We'll call this equation 7. This implies that t max, by t max again, the time taken to reach the maximum displacement, is equal to pi divided by 2 times omega d. All right, so finally, solving for x max, this would be x max is equal to x of t max is equal to, well, we know the sign is going to be 1, right? Because the sign function at this point is 1. If you substituted this value in for t here, you would get 1. You'd get sine of pi by 2. I'm not even going to look at that. So we know that this is v0 divided by omega d times e to the minus zeta omega n times t max, which is times pi divided by 2 omega d. Equation 8. All right, so you could just take these numbers now and punch it into a calculator, but I think I'm going to go one step further than that, since I'd like you to get your hands a little bit dirty with coding. I think it's very important for structural engineers to have some coding ability. You're going to need it time and time again. So I thought I would write a piece of Python code and show you how to solve it, and then beyond that, how we can actually turn this into a design problem to give us a little more insight into what's going on. I guess you could easily solve this problem by punching it into a calculator, but a couple of things. The first is sometimes you make mistakes and you've got to type it in over and over again. This makes it very easy to see what you've done. And I wanted to further convert this into a design sort of problem, which would actually give a little more insight into what is going on with this mass damper system. So we'll start off by writing down what we've been given, and that is that the mass is equal to 2,000 kilograms. So we'll put that as 2e3. In fact, let me just remind us that that's in kilograms. That's just a comment. The stiffness of the spring is 60 newtons per millimeter, which would be 60,000 newtons per meter. C, which is the damping constant, I'll call it capital C, is equal to 20 newton seconds per millimeter, which would be 20,000 newtons times seconds per meter. And by the way, it might sound like I'm pounding on my keys. I'm not. I apologize for that, but I've got a very, very sensitive mic that's sitting here on my desk, and I should really have a shock mount or an anti-shock mount for it. V0, the initial velocity, is given to us at 10 meters per second. Okay, and now we can calculate a few things. We know that C critical, we'll call it C sub C, is equal to 2 root mk, 2 times square root of m times k. And we don't have a square root function, so we need to import that. Or in fact, let's do it this way. From math, import square root. That will allow us to use the square root, just like that. Take out the spaces. So it's 2 times the square root of k times m, or m times k. And omega sub n, I don't have an omega, so I'll call it w sub m, is the square root of k divided by m. Zeta, which we'll just write out since I don't have a zeta, is equal to c divided by c critical. The damped frequency, omega sub d, is equal to the natural frequency, omega sub n, times the square root of 1 minus zeta squared. 1 minus zeta. To do a squared in Python, it's like that. It's 2 asterisks. All right, and Tmax, we showed this previously in this problem, is equal to pi divided by 2 times omega d. So pi divided by 2 times omega d. And we should import pi as well. That's part of the math library. Okay, that's pretty easy. And then x max is equal to v0 divided by omega d times exponential minus zeta times omega n. Let me see how I want to do this. It's zeta times omega n. I'll do it this way. Just times T max. Previously in the problem, we substituted this in for Tmax. I could have done it, but since I've calculated it right here, cleaner just to write it in. That's the beauty of using Python. Okay, and now we want to print out the answers. So let's print out a few things. First of all, let's just print out everything we've calculated. Let's just print out everything. So we'll print out K. We'll print out omega sub n. We can print C critical. Oops. C sub C. Print out zeta. We can print out omega sub d, the damped frequency. And of course T max. And finally X max. Oops. That's it. So I'm going to go ahead and run this. It's just Command B on my computer. And down below here in the console, it should print out all these results. So I've got an extra period here in line 6. Let's do that and run it again. Error V0 is not defined. Oh, because I did it as a capital V. Let me make it a small v up top here. Exp is not defined. I need to import that from the math library, I should say. The exponential function. And then finally it runs, okay? So K is 60,000. Our omega n is 5.477. That would be radians per second. C is 21,908. That would be newtons times seconds per meter. Zeta, which is the damping ratio, is pretty high. It's 91%. Damped frequency, you can see, is somewhat less than the natural frequency. That was expected. And the maximum time, the time taken to reach the maximum displacement is 0.7 seconds. And the maximum displacement is 0.13 meters, or about 13 centimeters. So when this car or this train or whatever it is, this mass hits the buffer, it's going to displace at a maximum of 13 centimeters. Now, part of this is a design problem where you might say, oh, I don't want it to displace as much as 13 centimeters, or I don't want it to take as long as 0.7 seconds to come to rest. I would like it to come to rest in half a second. How stiff would the spring need to be in order to achieve that? So I'm going to change this code up just a little bit to accommodate that. Let's see how I want to do this. Okay, so first of all, let's take all this here and we'll put it into a for loop. So what I'm going to do is say for k in, I'm going to want numpy here as well. So that I can use the arange function. Arange, and we want to go from, say, let's just make it 55,000 to 100,000. In fact, we've got 100,001. Why? Just because I'd like to include 100,000. And with the range function, this is not inclusive. Okay, enough about that. We can take away k up top here since we're putting it in the for loop. And then all this code below, I remind you that in Python, in order to include something as part of a code block, we just indent it. So there we go. The white space is important. So now what it will do is it will run through this, and it will loop, clean this up a bit, it will run k from 55,000 to 100,000 in increments of 5,000, and it will calculate all of this each time. And this is where Python starts to come into its own versus using a regular calculator. So very simple change to the code, and now I can run it for all these cases of k. In fact, let me just add another print statement here to leave a line between each one, and try it one more time. Okay, so starting at the damping ratio, and all the way on the other end, we see that at k equals 100,000, that the damping ratio is 0.707. It's about 71%. All right, so it's a little bit hard to look at that and see what's going on. So to make one more change to the code, what I think we should do is we should plot this. And the way we plot it is by using a library called matplotlib. So we want to import matplotlib, matplotlib.pyplot as PLT for short. And then we would like to store certain values. So we would like to store, what would I like to plot? I'd like to plot x and t. So x and a list for t, whoops, outside of this loop. And then what we're going to do at each time here is we're going to append it. So we'll say that t append, what do we want to append? We want to append t max. And same thing, x dot append x max. The reason we're doing this is so we will have a list of all the x's and all the t's. It will take a little bit longer the first time. And there we go. So the idea is I want to store t max and x max for each one of these cases. All right? And the idea of storing it is so that I can plot it later. So we're going to run through this loop. We're going to append all of that. I then need my k values, which is just this. And the way to do it in Python is just create a list of the k values as follows. K is equal to I for I in this range. So in other words, this produces a list. By saying for I in this list, I'm saying I will go incrementally one by one through the list. And in each case, k will equal the value of I. Okay, I don't want to have to explain more than that about Python, but fundamentally what I've done is I've taken all my k values, I've stored all my t values here and all my x values here, and now I just need to plot it. So how do I use PyPlot? Very simple. plt.plot k versus x. Whoops. And now all I have to do is say plt show in order to show the graph. Wow, I'm making a lot of typos today. Now when we run it, there's the plot of k versus x versus k. So I've got x on the vertical axis and k going from 55,000 to 100,000. Okay, so that works. Now let's just make it look a little bit better. We'll dress it up a bit. In fact, what we'd also like to do on the same plot is show k versus t max. All right. Let me set the limits. This is just a little bit of extra dressing. So I want to take the minimum value of k to the maximum value of k, and what I've left out here is the x limit. So on the plot, I want to set the scale of the x-axis, the x limits, from the minimum value of k to the maximum value of k. Let me add some scale here. So the y ticks, and I know this, by the way, because I played around with it before. We want it to go from 0.0 to 1.0, so that's the time taken, and we want it in increments of 0.1. So that shows me the intervals on the y-axis. I'd like to put a grid over here because it makes it easier to read. So plot.grid is true. And let's put a legend. Plot legend. And the legend would simply be, well, we've got x, we've got t, and then we'd like to locate it in the lower right. So we'll say location, lower right. Then finally just label the axes. So the x label is spring stiffness, which is k, and that's in units of newtons per meter. And then the y-axis would be the y label and the maximum displacement and corresponding time. So let's just write that out. Maximum displacement and corresponding time. Let me fix that typo. The displacement, of course, is in meters, and the corresponding time is in seconds. All right, and that is it. In fact, that's not the label, that's the title. I made a mistake. That's the title of the chart. So let me recap. I've said I want to plot k versus x. That's the first line. I've said on the same chart, plot k versus t, the time taken to reach each x. I wanted to set the x limits, the limits of the x-axis between the minimum and maximum values of k. I wanted to make ticks. I wanted the scale on the y-axis to be 0.0 to 0.1 in increments. Let me say that again, 0.0 to 1.0 in increments of 0.1. This line puts a grid over the chart, makes it easier to read, in my opinion. This sets up the legend. I've said there are two values that we're calling x and t, and the location is in the lower right corner of the chart. Label the x-axis as such, put a title, and then finally show the chart. Okay, that's it. Now we can run it. Something's not quite set right. Oh, I've got a typo somewhere. I used PLY down here on line 42. That should be a PLT. Sorry about that, not a PLY. But debugging is part of the process. All right, and there we go. Now we've got this code. Let me move this onto the screen, and here is our pretty looking chart. Let's just take a couple of minutes to discuss it. So first of all, the blue line is x. That is the maximum displacement. The green line is the time taken to reach that maximum displacement. And let's try to get an idea of what happens. So as the stiffness of the spring increases, so the maximum displacement increases. Does that seem a bit counterintuitive? It does, right? Because why, when it's getting stiffer, would it displace more? But I remind you that what's happening as it's getting stiffer is we're getting further away from the critical damping. So in other words, the damping ratio is much less. We showed that numerically. You could see it here on the right. The damping ratio is much less. What did I do? Let me run it again. So what's happening is, as there's less damping in the system is actually displacing more, despite the fact that the spring is stronger. Pull this back onto the screen. All right. And similarly, as the spring gets more stiff, you might think that kind of makes sense that it would take quicker to get there, right? So when there's more damping, this is down here where the spring is about 55,000. The time taken is much longer. Why? Because you're much closer to critical damping. So said differently, if there was no damping at all, you might imagine that the time would be very quick to get to the maximum displacement. So that's in fact what we're seeing, is that as the damping ratio decreases, the time to get to Tmax, the green line, decreases, and the amount of deflection increases. It's counterintuitive when you think about it in terms of the spring stiffness, if you just think about it physically. But if you think about it in terms of the damping ratio, then it makes a little more sense. Anyway, feel free to play around with this. I've made the code available. The link is below. It's on GitHub. Thank you very much for watching. I hope you found something useful in this video. If you did, please go ahead and give us a thumbs up. We'd love to hear your comments down below. And thank you for watching this video, and we'll catch up with you in the next one.